Today we will be looking at number systems. So here we have a table of contents to introduce in order the topics that we're going to be talking about. First, let's have an introduction to number systems. A number system is a way to represent numbers using symbols. We have counted in the number system with decimals, so base 10, in all of our lives. We represent these numbers using 0 through 9. This right here is actually incorrect. This should be a 0. I will change that. We add a number to the left when we run out of digits. So if we're counting the number 10, we cannot do that with one simple position. We have to add to the left, which is a 1 and a 0 is equal to a 10. This number is worth 10 times the 1 on the left. So yes, we have the 1 and then we have 10. Let us look at the number 189 for an example. 189. First position, 0. So 10 to the power of 0 times 1 is 1. Then we have the symbol 8 in the first position, in the second position, sorry. So 10 to the power of 1 times 8 is equal to 80. Finally, 9. 10 to the power of 2 times 9 is equal to 90. Let's look at binary. Binary works in the same way. So binary works in the same way. Only we can only use ones and zeros, and it is in base 2. The reason for this is that computers functioning with electricity. If a transistor allows a current to go through, the current is interpreted as 1. If there is no current allowed through the transistor, it is interpreted as a 0, and that's actually how computers work. So let us take the number 15 and write it in binary. Number 1, we have the first position, which is 0 to the power of 0 times a symbol 1 is equal to 1. Second position, 2 to the power of 1 times 1 is a 2. Third position, 2 to the power of 2 times 1 is a 4. Fourth position, 2 to the power of 3 times 1 is an 8. Next, we have octal. As shown as the previous number systems, we can create number systems based on any range of symbols. Another popular number system is octal, due to more numbers being divisible by 8 and 16. But 16 is hexadecimal, which I'll explain next. Octal uses symbols from 0 to 7 and uses base 8. Let us look at the number 235 in decimal and octal. So this is in decimal right here. I'm going to convert it to octal. So it is 353. First, we have the first position. 8 to the power of 0 is 1 times 3 is 3. Next, we have the number 5. 8 to the power of 1 is 8 times 5 is 40. Symbol 3 in the third position, so 8 to the power of 2 times 3 is 192. We add up the numbers. 192 plus 40 plus 3 is 235. Finally, we have hexadecimal. As the name suggests, we use 16 symbols, but we do not have more than digits that go from 0 to 9. So, instead of inventing symbols, we simply add capital letters in alphabetical orders. The hexadecimal uses the digits 0 to 9, 0 through 9, and the numbers 0, A, B, C, D, E, F. The value of the letters continue as A, 10, B, 11, C, 12, D, 13, E, 14, F, 15. So let us look at the number 1678 in hexadecimal. First we have E. E is valued as 14, as you can see from this. So 10, 11, 12, 13, 14. In the first position, 16 to the power of 0 is 1, times 14 is 14. Second position, 16 to the power of 1 times 8, which is the symbol that we have here, is 128. In the third position, 16 to the power of 2 times 6, which is our symbol, is 1536. 14 plus 128 plus 1536 is 1678. This is a table that you can use to compare decimal, binary, octal, and hexadecimal, even though you cannot compare hexadecimal extensively as we do not have the letters here. Let's look at binary. So binary addition. We have simple and carrying, and this is going to apply to every single number system. Just like in our decimal number system, we have simple addition where we do not require carrying any numbers, and we have addition in decimal where we require to carry over a number. Let's start by analyzing simple. We have a 0 plus a 1, we have a 1. We have a 1 plus 0, that's a 1, 0, 0 is 0, 0, 1, 1, 1, nothing, 1. In this case, we have to carry So 1 plus a 1 is a 2. But you see, we cannot use the symbol 2. To the value to the left, a 2 here is worth a 1 here. So we carry a 1 over. We have 1 plus 1, once again, 2. We cannot do that, we carry over a 1. 1 plus 1 is a 2. We carry over a 1, and we are left with a 1 here, which we carry down. Same reasoning here. We have a 1 and a 1, which cancel out to a 2. We carry it over, we're left with a 1, 1 and 1. Now let's look at subtraction. So just like in any other number systems, we can borrow from the left. The digit from the left is worth the base times to the number to the right. Meaning, in our case, in binary, a number to the left is worth the base, which is 2, to the number on the right. So borrowing a 1 from the left digit is worth 2 for the right digit. This is because binary is base 2. So let's look at this addition where no borrowing is, this subtraction, where no borrowing is needed. 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1, and 1 minus 1 is nothing, 0. We do not have to write this number right here. Next here, we have borrowing, which is needed. So we have a 0 minus 1, we cannot do that, so we borrow from our left. Now remember, when we're borrowing from our left, first we turn this into a 0 right here. We carry over here. This number to the right is worth a 2, so we subtract a 2 minus a 1 and get a 1. Now here we are left with a 0. So what are we going to do? We're going to borrow from the left. We cannot borrow from the left, so we borrow another over. We have a 1 here, which we turn into a 0. Here, this number is worth a 2, but remember we're borrowing here as well. So this is a 1. 1 minus 0 is a 1. And here we have another 1. 1 minus 1 is equal to 1 here. And here, so here we left off here. Here we have to borrow a 1. So we borrow from the left. We cannot borrow from the left, so we borrow from another here. This 1 here is turned into a 0. We have a 2 here, but we have to borrow a 1 here, so 1 minus 1 is 0. We're left with a 1 here. We carry down. That's a 1. This is a 0. 0 minus 0. 1 minus 1. Nothing, nothing. Next, we move on to adding octal, which is very similar. 7 plus 1 is an 8, but we cannot use the symbol 8, so we simply transport the 8 as what is worth a 1 to the left column, which is a 1. 1 plus 4 is a 5, plus a 6 is 11. Here we have a 0, 11. Since we cannot put down the number 11, we can only use the base 8. So we subtract 11 from 8 and we get a 3. We have a full 8 that we carry over, which is equal to a 1 on the left. 1 plus 1, 2 plus 2 is a 4. 4, 3, 0. Now for octal subtraction, it gets a little bit more interesting. So we have a 6 minus a 7, we cannot do that, so we borrow from the left, which was a 5, which we turn into a 4. The 1 here is worth an 8 on the right because we're talking base 8. So 8 plus 6 is 14, minus 7 is a 7. 4 minus a 5, we cannot do that. So we borrow from the left a 3. We turn that 3 into a 2. That 1 that we took from here is worth an 8 on the right. 8 plus a 4 is 12, minus 5 is a 7. 2 minus a 1 is a 2. To add hexadecimal, it gets even more interesting because we have the alphabet. Here's the actual values of the alphabetic letters that we are using. So 8 plus a 3 is an 11. So we simply place on a B. F, 15 plus a B, 11 is 26. So what we do is we subtract 26 minus 16 and we are left with 10. So we place down A and we carry over that 16, which is equal to a 1 on the left side. 1 plus 3 is a 4, plus 5 is a 9. Subtracting hexadecimal is even more fun. So we have an A equal to a 10 minus a 2 is an 8. Next we have a 5 minus a 7. We cannot do that, so we borrow from the 3 a 1. That 1 is equal to a 16. On the right side, 16 plus a 5 is a 21 minus 7 is 14, which we get here, and we place as an E. 2 minus 1 is a 1. Finally, we have positives or negatives, so this is only for binary. If the first integer is equal to 0, the number is a positive. If the first integer is equal to 1, the number is a negative. These indicators are not actually counted when figuring out the value of a binary number. And just as a fun fact and application to real life, number systems are actually applicable in URL codes. So you will often see that in a URL code, you will have something something something.com/ and then you'll have numbers and you'll have letters. Those numbers and letters are actually in higher number systems, in 32 base, in 64 base, and they basically simple down a large, very large number that identifies a web page. Fun fact of the day over, and thank you for watching. Here we have some links that I think you will find useful. A Quizlet to test your basic knowledge, and a Kahoot to apply the knowledge. You will finally have an assignment, which is basically a test on number systems. Thank you.